Welcome to the video on the dot product. So the dot product really is kind of an extension of multiplication. Multiplication for scalars, so for any numbers that you have been dealing with, is very simple because you get introduced to that very early on in elementary school, and most likely even earlier than that, depending on how mean your parents are to you. So you're going to run into that multiplication. But when you're studying vectors, you have noticed that, hold on a second, I've been doing addition of vectors, I've been doing subtraction of vectors, which is really addition with the opposite vector. I've been doing multiplication, but I've been doing multiplication by a scalar. So I've been scaling my vector either up or down, depending on what I want to be able to do. But I didn't actually do any kind of multiplication with regards to vectors. And what I mean by that is we never did anything like this, or you have never done anything like this, where you have a direct multiplication. Because with vectors, you have to be very careful that this symbol that we use for multiplication is actually something which you call a cross product when you're talking about vectors. And that's something you'll get into, and I'll be doing video on that as well. However, what we have is, instead of just pure multiplication, we are going to be talking about this magical dot. So we put this dot within two vectors, kind of right in the middle. And what it means is this, right here. So if you have two vectors and you want to be able to find what the dot product actually is, it will be simply what the actual magnitude of the first vector is, multiplied by the magnitude of the second vector, and then multiplied by the cosine of the angle between the two vectors. So you can imagine here, so I have drawn two vectors. It doesn't matter actually in what orientation these are. So, I can swing this around anywhere I like. The actual magnitude doesn't change, and certainly the angle between them doesn't change. And the dot product captures the magnitude of one multiplied by the magnitude of the other, and then it multiplies by the cosine of the actual angle in between. That's what it's simply doing. Now, what's interesting is it's not very difficult to apply this. So here is an example right here. So I have my two vectors. So I'm going to just say this is V, and it is going to get dotted with U. So here are my two vectors. And if I wanted to be able to find out what its dot product is, then I'm just going to take the magnitude of the first, which is going to be 6, which is given there. I'm going to be multiplying it by the magnitude of the second, which is 3.5. And then I'm going to take the cosine of the angle in between the two vectors. Now, if you do this, you will notice that the result is actually a scalar. So it converts your actual two vectors to a scalar result. Now, there is some intuition and a need for this, very much so in physics. So you're going to run into some applications of that, and I'll do some of those as well. But for the moment in this video, I just want to give you the gist of this operator. So think of it as simply like an addition or a subtraction that you have done in the past. And the dot product just has a very direct, particular definition that you're going to be applying. Now, if I finish this off, so I can take out my calculator in here. So, I can take 6 multiplied by 3.5, and then I can multiply by, I guess, the cos of 20. And I'm going to round this off. So let's say 19.7. Now, these particular vectors, they didn't give me any units. Okay, so this is kind of unitless completely. But if you do have units and you start multiplying, then you have to think about that as well. But for the moment, we'll assume that there are no units in here. Once you do applications, then the units are going to start coming at you. That is really what the dot product is. Now, in this case, we have kind of represented this by the knowledge and assumption that we know what the magnitude is, and we also know what the angle in between here is. But that's not always the case. For example, if you're going to be representing your vectors in Cartesian, as Cartesian vectors, so I can put up a link up above there to the Cartesian vector introduction. In those cases, you know that your vectors are going to take on an x and a y value. And now doing their product in between them actually becomes a little bit strange. Now, you can certainly still calculate it in the way that we have, but okay, let's break down the Cartesian representation of these particular vectors. So let's assume, so I'm going to be taking this definition right here, and I'm going to be translating it back. So let me copy this. I'm going to bring it down here actually. And I'm going to be translating it back to the actual, so let's assume that this right here, okay, to its actual coordinates. So let's make this Vx and let's make this Vy. So those are the components of that vector. And then let's make this to be the vector of Ux, comma, Uy. And that would have been its Cartesian representation. And now if I put a dot product in between here, between this V and this U, then what is the actual dot product? Sure, I can find the magnitudes very easily. We know that the magnitude of any vector, so for example, the magnitude of V, if I know what its components are, I know that this is square root of simply Vx squared plus Vy squared. So that's the magnitude. And I can do the same thing with U. So that's not a problem. The problem becomes, all right, well, what is actually the angle in between these? And I would have to find that angle. Now, we can still find the angle, right? We have the tools, especially if you've studied trigonometry, and by this time, if you're doing vectors, you definitely have. Then we can find what that angle is. But I'm going to just show you what happens here if I'm going to break these things down. I'm going to take this right here and I'm going to copy it. I'm going to bring it down in here, paste it. Now I'm going to shift it around just so that it looks a little bit better for me. So let's put it like this. So this is going to be V, okay, and U. And now what I'm going to do is I'm going to create a resultant vector in here. And that resultant vector, okay, so let's say I'm going to create this vector right here, right across from my angle. And I'm going to call this the resultant vector. Now this resultant vector, the way that I have drawn this, then really that resultant vector is actually, okay, so if I would take this out, this would have been simply V minus my U, so the opposite, okay, of that. And that shouldn't shock you in any way. So here, if I do this, I'm going to duplicate it, right? So notice what's going to happen here. I'm going to just kind of shift it back all the way, click it in place right there. And you notice that indeed, so for this vector, I'm going to duplicate it. So using the parallelogram, okay, we notice that indeed that is my R. So my R is simply just V, okay, and then the opposite of U, so adding it or subtracting it. Now, this is going to be useful for me to be able to find out what the dot product actually is. Now, before I begin, let me just remove this for the moment, now that you hopefully understand what that is coming from. What I'm going to do is I'm going to try to find kind of the dot product from these Cartesian coordinates. So bear with me for the moment. First thing I'm going to do is the following. I know by using the cosine law that I have R, this is going to be the magnitude of this squared. It is equal to, so by the cosine law, it's going to be V, so the magnitude of this squared, plus the magnitude of u squared minus 2, and then the magnitude of v multiplied by the magnitude of u. And this is going to be cos of the angle that I have in there. Now, this is promising because right here, so this, if you take a look at this, well, this is nothing else but simply the actual dot product in between. So let me kind of rearrange this. And what I'm going to do, this is just purely for convenience. The magnitudes I'm going to drop, so because I don't want to just keep drawing or writing out those lines. And then I'm going to drop the actual vector symbol. But these are all actually magnitudes. All right? So instead, what I'm going to do is I'm going to just simply write it like this. This is just purely for convenience so that I don't have to continuously write out everything within those actual absolute values, so the magnitudes. And I don't have to draw the arrows above to designate a vector, but these are all indeed the magnitudes themselves. Now, rearranging this, so I'm going to bring this whole thing over to the other side. So what it's going to give me is the following. I'm going to have 2. This is going to be the magnitude of v times magnitude of u. Cos theta is equal to, and this is going to be v squared plus u squared minus r squared. And dividing by 2 on both sides, this is going to give me v times u cos theta is equal to, and this is going to be v squared plus u squared minus r squared, all over, so this is all over 2. That's what I have there. But I just said that all of this, well, this is just simply the dot product in between here. And that's exactly what I'm trying to find, what that dot product is. However, I'm trying to find the dot product in terms of its Cartesian representation. So here we go. Now what I'm going to do is I'm going to take the following. Now I know what the actual magnitude squared of v is. The magnitude of v is nothing else but its component. So this is going to be vx, right, squared, plus vy squared, and then it's the square root that is the magnitude. But because I'm squaring it right here, so that square root falls apart. That's my first component right here. Now it's going to be next, so this is going to be plus. Now my second component, which is the u, so plus this, I'm going to write it actually just below it, and this is going to be now ux squared plus uy squared, and that's my second component. Again, it's the magnitude squared, so that square root falls apart. And then finally, it's going to be minus, so now it's the whole thing, okay, which is going to be subtracted. I'm going to put a subtraction, that's this right here. And now it's my r. But what is my r? Well, hold on a moment. My r, so if I go back in here, my r is right here. That's my r. So it is the subtraction between v and u. And that is nothing else. And if you would write it out in terms of its components, then this is going to be the vector. So this is v x minus ux, comma. This is going to be vy minus uy. And that's the actual vector. That's this vector right there with those components in its Cartesian representation. And now, if I want to take the magnitude of that, well, what that's going to be is the following. So I'm going to have, this is going to be vx minus ux squared plus, and this is going to be vy minus uy squared. Now, it's going to be in the square root, but it's r squared right here. This is all r squared. And because this is going to be r squared, that again, that square root falls apart. And the whole thing is being subtracted right there. Now, let me expand, okay, what I have there in blue. If I'm going to be expanding that out, that's going to be Vx squared minus 2 Vx ux plus ux squared. That's just the expansion of the squared. Now it's going to be, so now this plus, so this is going to be plus. Now it's Vy squared minus 2 Vy uy and plus, finally, uy squared. That's the entire expansion of all of this. So all of this is equal to this. Now I do have that negative sign, and now let's not forget that we are dividing the whole thing by 2. What I have done here is this is just the numerator right there. So this entire thing is just the numerator, which is on top, and I'm going to be dividing by 2. But look what happens here. Because of this negative right here, then you have Vx minus Vx, both of them are squared, so that falls off. This is gone. Now Vy squared minus, and now you can take a look, so Vy is right there, so that is gone. Ux squared minus ux squared is gone. This, okay, is going to be gone with this. And your numerator now, because of the fact that we have this negative in here, what it turns out to be, so that negative, if you bring it in, it's going to cancel this negative and this negative. And that's just simply going to be 2 Vx ux plus 2 Vy uy, and this is all divided. Now I can bring back that 2. And now this 2 and this 2 is gone. And look what is left behind here. So if I write this whole thing out now, then what I have is this is nothing else but it is equal to Vx ux plus Vy uy. So that's the right-hand side, and my left-hand side is right here. That's my left-hand side. So your dot product, if you are dealing with the actual Cartesian coordinates, it's nothing else but just multiplying the x components and then multiplying the y components and then adding them up. So we don't even have to find what the angle is. We don't need to know what this angle is right here when we are working. So this cos of this angle theta just falls apart if we have it in Cartesian coordinates. So let me just show you. I'll give you an example of this. So I'm going to just add a page in here. So what I'm saying is the following. If you have your vectors, so let's say maybe it's 1, 3, and you want to find the dot product with another one, doesn't matter, it can be negative, so let's say we have that. The dot product between these, if it is in its Cartesian coordinates, or if it's broken down into its x and y components, by this right here, because that is the dot product in those coordinates that we have there. So this is simply 1 times negative 2, which is going to be negative 2, plus 3 times 5, which is going to be 15, and this is equal to 13. And you have just found your dot product. So it's a scalar value in here, and it's equivalent to 13. That is wonderful, right? We don't even have to find any coses, okay, of any angles. So if it's broken down into its components, that's all that you have to do. And you can do that with anything. So, you can certainly have any style, okay? It can be as complicated as you like, but as long as you're taking the dot product in Cartesian coordinate form, if you have anything of that nature, then it's simple. Just go ahead, multiply the actual components. It's going to be 50, and then you add, okay, your y components. It's going to be 25, and there is your dot product. That's super quick. And that falls off because of this proof, okay, that I have just shown you to break down the vectors into its components of x and y. That's what you would have there. So I hope that you find that useful. Now, in general, indeed, our definition of the dot product between any two vectors indeed is the magnitude of the first vector multiplied by the magnitude of the second vector and then multiplied by the cos of the angle in between them. Now, we have to be careful that here now, this dot, as you now study vectors, you are aware that, well, for scalars that you have, it just simply means multiplication. But for vectors, it takes on a very special meaning. So we actually try to avoid writing these dots. And we just simply know that in between brackets, there is a multiplication. All right, so that's the dot product in its definition. And now we've applied it to a few examples. And this dot product has several properties. Now I want to be able to do these properties within here. So I just kind of wrote them down before I was doing the video. So here are the properties that you have. Now the first property is with regards to perpendicular vectors. So two vectors are perpendicular if and only if their dot product is equal to 0. This shouldn't shock you in any way. Because if you have two perpendicular vectors, right? If you have one vector and the other one perpendicular, okay, is the other. Now, perpendicular means there's a 90-degree angle in between them. Well, by definition, if you're trying to do the cos of the angle, and the angle is 90 degrees in between, well, of course, cos of 90 is equal to 0. So it doesn't matter what their magnitudes are. The angle between them, if it's 90, cos of 90 is always going to be 0. And this is exactly what you're going to find. So the dot product is going to be actually equal to 0. Now, the second property is the commutative property. This one you have seen in addition, right? Where you can just add two particular numbers, so you have commutative property. You've seen it in multiplication of scalars, okay? So scalar numbers, you can definitely multiply, right? Doesn't matter what the order is. If you put the first number, the second number, multiply them or swap them and then do the multiplication, that's the commutative property. Well, the dot product also works the same way. So it doesn't matter which vector is first, which vector is second. You just simply are multiplying these through. And again, this should not shock you because of the fact that if you're going to be doing this, and by definition, we know that it is the actual magnitudes in between here multiplied by the cos of the angle between them, then it certainly is exactly the same thing if you just take u and then you take v. You take the magnitudes of those because all you're doing is swapping them, and the angle in between them, it doesn't change. So that commutative property works. So you can do that dot product if you like. Now, the third property is the associative property. And this one is if you are given a scalar. So we typically use a scalar k. So if that scalar is some number, okay, so some real number, and now what you do is you scale one of the vectors. So you simply are scaling this. So this is going to be k multiplied by the vector. And notice I put brackets in there. And then you take the dot product with another vector. It's exactly the same thing as just simply removing that scalar outside, doing the dot product first. So you can take the dot product between, and then you multiply the dot product by k. That's going to be the same thing. And that k is exactly the same. So you can bring that k over to the other vector. So you can scale the other vector and then do the dot product. This is the associative property, okay, with regards to these particular two vectors. Now, the fourth one, the distributive property that we have, this one is pretty neat because if you notice, so here, I have three vectors. Now, I've called one of them v, and then the other two I called u, except one is u1 and the other one is u2. And what we have in here is this very much looks like the distribution across any time you were, for example, doing distributive for some kind of polynomials, right, that you would have, okay, and then you would be distributing across, and this just simply means multiplication. So this distributive property looks like it's acting like multiplication, where we can bring this inside of the bracket and then do the dot product with each particular vector. Right? Now, we would do this with each term if you were doing polynomials or whatever. Binomials, doesn't matter. So in those cases, we're doing multiplication by terms. Here, we're dealing with vectors. And yet, the dot product distributes across the bracket. And now notice that you can distribute it across the bracket, and then you can use the commutative property. So notice you can just swap it. So I just swapped the v and the u1. And I can do the same thing for swapping the v and the u2. And then I can take out the v outside from here. And you notice that, it doesn't matter if the v is first, okay, or if the v is last in terms of that dot product. So that distributive property is super useful, and it works the same way as you did it with terms. The last property, this one doesn't really necessarily have a name, but this property just simply tells us that if you take the same vector and you multiply it by itself, then the result is just the magnitude squared. And again, no big deal. This isn't anything revolutionary, because the dot product by definition means that you're going to take the magnitude of one times the magnitude of the other one, and then the cos of the angle in between. Well, but the angle in between the same vector, this angle is just 0, and cos of 0 is just simply equal to 1. So if that's equal to 1, then of course this is just going to be the magnitude squared, because it's just v times v itself, at least the magnitude of that. Those are the actual properties that you will be thinking about, okay, of this dot product. This is as far as I want to be able to take it within this video. I think it gives you a good sense. It defines the dot product for you. I haven't done it through actual applications. I'll do that applications in other videos. And here my interest was to define the dot product, to present it to you both from the viewpoint of vectors that are in kind of geometric form, and then to present it to you if they're in Cartesian vector representation. And you notice that all you have to do right here is just simply multiply the x components and then add it to the multiplication of the y components. And then lastly, I gave you the properties right here, and that was the perpendicular vector property. So the dot product is 0. The commutative one, we can swap the dot product. Okay, so we can swap the vectors. We can have an associative property with respect to multiplying by a scalar k. So you can bring it into the vector, or you can take it out. You can distribute the dot product across vectors when they are adding together. And this doesn't mean just only two vectors being added together. It could have been three vectors added together, and you can just distribute. And then the last one is very simple, that if you take the dot product of a vector multiplied by itself, the result is magnitude squared. That's all. All right. Thanks for watching, and I hope that I'll see you in a future video. Bye, everybody. Take care.